Good morning, everyone. I am very happy to share our paper today. So the motivation of our work is that consistent low frame latency is very crucial in live video analytics applications, but very challenging to achieve in real world because of the dynamic wireless channel in the video content. So what we're doing is co-designing the application and the radio access network for end-to-end scheduling of the video analytics pipeline. And let me tell you in detail how we do that. So as you all know, there have been a lot of live video analytics works in recent years, but they have been mostly focusing on optimizing the average throughput. So actually, our goal is to optimize the per frame latency. And let me tell you some example scenarios why this is really important. So first of all, consider an autonomous driving vehicle running at 40 kilometers per hour. If the vehicle wants to make decisions every 1 meter, it should be able to analyze the live video frame within 100 milliseconds. Similarly, in an AR person finding scenario, the AR glasses should be able to track the moving target within 150 milliseconds so that the rendered bounding boxes and the actual location of the target is within 5% error of the field of view. So in recent years, multi-access edge computing, or MEC, has been getting increasing attention as a key enabler for low latency video analytics. So this figure shows the deployment model of our target scenario, which reflects the recent real-world deployment example from Microsoft and AT&T. So there are 3 parties involved here: the service operator who actually deploys the video analytics services, and the radio access network and the cloud operator that co-provisions the MEC target platform, like Microsoft Azure Edge Zone. So the service provider composes the video analytics pipeline, prepares the DNN models, and defines the application SLOs, and actually deploys the target cameras in the target sites, and connects them to the MEC platform that it has subscribed to. And now at the runtime there, the operation is composed of 2 stages. First, the network stage, which involves live video streaming over the wireless network, and the compute stage involving DNN inference at the edge server. So actually, the question we wanted to investigate here was, can MEC platform alone guarantee low and consistent frame latency in practical environments? So actually, we conducted a real-world measurements over commercial 5G MEC platforms, and the answer was no. So actually, when running this person monitoring workload over AWS wavelength zone hosted in Seoul, we noticed that the end-to-end latency is typically very fluctuating, and the latency SLO satisfaction can drop quite significantly, for example, as low as 26% in high mobility scenarios. So actually, why is this happening? We analyzed that this is because the network and the compute latency both fluctuates very dynamically. So the network latency can be formulated as the video encoded frame size divided by the network bandwidth, and the compute latency can be formulated as the detection latency plus the recognition latency times the number of people in the scene. And as you can see here, the red terms there are all fluctuating over time, and we can see in the right figure that both latency is highly dynamic and causes frequent latency SLO violation. And I want to note that while in our work we currently target the traditional CNN-based workload, this kind of workload fluctuation is also prevalent in recent video language models as well. I would like to add some discussion on that towards the end of the presentation. So actually, recently there have been a lot of works on adaptive video analytics systems, but they are mostly limited because they design their schedulers on either only one of the application and the RAN side, which operates in a mutually agnostic manner with the remaining side scheduler. So for example, the application side only bitrate and DNN adaptation works suffer from long tail latency, mainly as because even if the application scheduler makes the decision, the RAN does not know the actual video frame size and the network deadline, and failing to provision the radio resource blocks in a timely manner. So therefore, as we can see here, none of the bitrate DNN configurations that we have satisfy the consistent low latency SLO, high SLO satisfaction rate. And on the RAN side, some recent works schedules the RB with application awareness. For example, Tutti exponentially increases the UE scheduling priority as the application deadline approaches. However, without the application layer bitrate control, that leads to this kind of scheduling leads to suboptimal resource allocation, because it often allocates RBs to a user with bad channel, because even though it allocates the RBs to a urgent UE despite the bad channels. So as you can see in the figure here, at the cost of very small increase in the SLO satisfaction, the overall throughput and fairness is quite hurt when we're trying to do this kind of like RAN-only scheduling. So then, why haven't people been designing this end-to-end scheduler over both the application and the RAN side? For example, we can formulate this kind of problem involving an end-to-end scheduling of the video bitrate, DNN, and the RAN resource block and the server GPU at the same time, given this application's accuracy requirement and the server and the RAN's resource budgets. However, a critical challenge is that in practical MEC platforms, it is provisioned by two split operators, the RAN and the cloud operators, that have disjoint control over the scheduling parameters. So for example, in this formulation, the cloud operator has access over the first 3 lines, whereas the RAN operator has access over the last line. And actually coordinating the two schedulers to work on a shared problem is very challenging, because not only each operator would like to grant the control of its resources to another scheduler, they would also be reluctant to disclose their scheduling algorithms, which is mostly operational proprietaries, like for RAN, the channel estimation or RB scheduling algorithms. So we design ARMA, or App RAN Mutual Awareness in short, to tackle the aforementioned challenges. So the core of ARMA is a mutually aware decoupled scheduling framework, which the overall operation flow looks like this. I'll revisit the specific operational details later, but here I'll just introduce the key features to deliver our core ideas. So actually, to tackle the split operator problems, we design decoupled app RAN schedulers that run separately on each app and RAN stages, but they split the end-to-end latency SLO to network and compute stages and allocate their own resources to follow their own SLOs, thus guaranteeing the end-to-end latency in a global manner. And as opposed to prior works that where each schedulers run in a mutually agnostic manner, we enable a mutual awareness for accurate resource estimation and allocation. And actually, in the foundation mechanism of ARMA for achieving consistent low latency is the bitrate DNN interplay. So let me illustrate how this works using this figure, and assume that this is a 2D bitrate and DNN configuration space, where the blue region here denotes the configurations that satisfy the application's accuracy requirement. And assume that we're currently using the configuration, the yellow star there, but the network bandwidth fluctuates and drops to that blue line. If we want to only calculate, adapt the bitrate only, we can only reduce the bitrate to as low as B1, which is still above the bandwidth limit, which would incur a latency violation. As opposed to that, we do an interplay between the video bitrate and DNN complexity, which can further reduce the bitrate to as low as B2, but compensating the accuracy drop from the lower video bitrate using a higher DNN accuracy. The converse also works for a compute bottleneck scenario, and thus guaranteeing a robust accuracy latency guarantee under complex latency fluctuation scenarios here. Yeah, so actually our approach sounds quite promising, but to realizing this as a real system entails several technical challenges. So first of all, we need to guarantee frame latency in units of video frames, but actually video bitrate cannot be controlled accurately in units of a frame granularity, because video codecs are typically designed to match the target bitrate at a average sense over 1 or 2 second video chunks. And actually, we need to adapt the video bitrate and the DNN according to the predicted network latency and compute latency, but the latency prediction is inherently error-prone, because we cannot estimate all the sudden and unpredictable network bandwidth drop or scene content changes. And finally, there's no signaling interface right now for the application and the RAN to exchange their information in a mutually aware manner. So we design ARMA with the following solutions to tackle the challenges. So first, we design a per GOP bitrate DNN joint scheduler, which predicts the network and compute latency over the next scheduling window, and selects the bitrate and DNN in a joint manner that maximizes the overall expected latency SLO satisfaction. And given the selected bitrate and DNN, we also design per frame schedulers that actually allocate the RB and GPU resources to finish the video streaming and the DNN inference within the deadline. And actually, these two schedulers have mutual compensation mechanisms to incorporate the unpredictable errors that occur at runtime. And finally, to enable mutual awareness, we leveraged the OpenRAN RAN intelligent controller for the app and RAN side schedulers to exchange their information. So in the next few slides, I would like to just briefly introduce the key insights of each component here. So the first component is per GOP bitrate DNN joint scheduler, whose goal is to select a bitrate DNN configuration that maximizes the expected latency SLO satisfaction over the next scheduling window. So for example, assuming the AR person finding scenario where the AR glasses is scanning a very complex scene, and assume that the network bandwidth is quite stable, whereas the compute workload fluctuates quite heavily. And assume that we have two bitrate DNN configuration pairs, which would then in such a case, which one should the scheduler choose? If we choose a lower bitrate, but instead a higher DNN backbone, this would result in a very high computation latency and fluctuation, and thus resulting in latency violation. And a more desirable choice is to use a more lightweight DNN, but use a higher bitrate because the bandwidth is more favorable. But however, given the bitrate DNN configuration, how can we predict how the network and compute latency will be in the next video chunk? So our idea is to build online stochastic latency models to predict each UE's network and compute latencies. And our key observation here is that the network and compute latencies are approximately Gaussian over a short window over time. So these figures actually show the QQ plot of network and compute latencies against the normal Gaussian distribution. So basically, a QQ plot is a scatter plot where each point corresponds to the ordered value from the source and the target destination. And we can see that the plot is aligned with the red line there, y equals x, indicating that the two distributions are quite matching with each other. So the latency distribution is approximately Gaussian. So actually, we did some analysis on why this kind of Gaussian modeling is possible. I won't go into the details, but for example, for the video frame size, is mostly composed of the residual signals that after the temporal video motion vector matching, which is essentially a random Gaussian noise. And actually, I won't go into all the details, but please refer to our paper on more analysis on this. Yeah, so based on this observation, at runtime, we keep track of the network latency at 1 megabits per second and the compute workload as the base latency modeling unit. And then we model the end-to-end latency of a given bitrate and DNN configuration like this. And one thing to highlight is that the network latency can be modeled as a linear relationship according to the video bitrate, mainly because the quantization process is a linear operation. And finally, with this end-to-end latency model, we can solve this scheduling problem where we schedule the bitrate DNN configuration over the UEs to maximize the overall latency SLO satisfaction. And one thing to note that is that while solving the RAN resource budget constraint, we need the spectral efficiency and the total number of RBs reported from the RAN side, because that is very crucial in determining what is the maximum bitrate that each UE can select. But this can't be accurately estimated at the application side only. So moving on, we have selected the bitrate DNN over the next group of pictures. We need to actually allocate the RB and GPU resources to stream the video and finish the DNN inference within the frame latency deadline. And actually, as I mentioned before, the latency prediction is actually error-prone, so there can be a perfect estimation here. And to compensate the errors, we designed two per-frame schedulers that have mutual error compensation properties. So first of all, the application-aware RB scheduler compensates the workload estimation error by latency SLO splitting, meaning we set a stringent network SLO when the workload fluctuates, so that the network streaming can finish early and leave margin for compute workload estimation error. Actually, we have also designed a SLO-aware RB scheduler to serve that purpose. I won't go into the details for that. And also, conversely, at the server side, deadline-aware GPU scheduler compensates the bandwidth estimation error with a preemption mechanism, where when a user's network streaming is longer than expected, it can preempt the other users whose network bandwidth was actually more favorable than expected, and the network streaming finishes more earlier. And finally, the final component is a signaling interface between the app and RAN schedulers. For this purpose, we leverage the RAN intelligent controller, which have been actively being standardized in the Open RAN community. And our key idea here is to exchange necessary scheduling information in a minimal obscured format that does not leak any operational proprietaries between the operators. So for example, the application to RAN interface only shares the frame size, network deadline, and the frame type, and hides the application video content or DNN models and so on. So putting everything together, the ARMA system architecture looks like this. So at the bottom side, we have the base data flow where the video UEs stream their video and run inferences. And the green components are the schedulers that allocate the video bitrate, DNN, the latency SLOs, and the RVs and GPUs. And the blue components are the resource monitors that enable this mutually aware scheduling. So we evaluated ARMA over two real-world testbeds. One is the over-the-air testbed composed of commercial off-the-shelf smartphones and SRS RAN 5G stack over USRP. And we also implemented a system-level simulator leveraging the SRS RAN's RF simulator for a more reproducible and controllable channel state manipulation, as well as support more number of UEs. So I'll briefly walk through the key results. First is the end-to-end latency comparison of ARMA against various state-of-the-art video analytics systems over the application and the RAN. And as we can see here, ARMA achieved 97% latency SLO satisfaction rate, which is notably 20% higher than the state-of-the-art baseline composed of application and the RAN scheduler that operates in a decoupled, mutually agnostic manner. Next, we also compared ARMA's latency against the decoupled state-of-the-art solution as the number of UEs increase. And we can see that the ARMA shows lower tail latency increase, which mostly comes from accurate bandwidth estimation from the RAN awareness. And lastly, I want to note that ARMA can be implemented with negligible overhead compared to the default proportional fare-based scheduler. For example, at a similar CPU overhead and 3% additional memory overhead. And please refer to our paper for more detailed evaluation results. So before finishing the talk, I would like to discuss some points for future research directions. So first is on the generality. So as I mentioned before, while we mainly target a traditional CNN workload here, we also find that the compute latency fluctuates with regard to the scene complexity, even for state-of-the-art recent video language models as well. So for a simple example, if you put a scene description query to the video language model, the output response length will be proportional to the scene complexity and increased latency, inference latency. But actually, the specific relationship may be more complex and non-trivial than the linear relationship with traditional CNN workload and would require a more sophisticated latency modeling. And I also want to finally note that while we have shown promising results in a lab-level prototype evaluation, there's a lot more to do for the actual deployment of ARMA in practical environments, including handling resource availability fluctuation on the server side due to background competing tasks, handling multiple concurrent application flows within the same UE, and actually some standardization efforts of our RIC implementation into the actual Open RAN standards like the recent ORAN DApps or Microsoft Dynamic Service Models and so on. Yeah, so in summary, ARMA is an end-to-end scheduling system that achieves consistent low latency in MEC live video analytics, and we believe ARMA is a compelling example of using the emerging Open RAN standards for real-time AI applications. And actually, there's a lot of challenging and interesting future research directions that we need to tackle, so please feel free to drop me a note for more discussions. Thank you very much.
Thank you. Okay, don't be shy. Come on for questions. Let me maybe start while we have the first person ready. I have this general question about scalability. I know you presented a result there with 8 UEs, but as you can imagine, with more UEs, you're going to have more complex behavior. Latency prediction becomes harder. So do you think there's a scaling limit there at some point?
First of all, I think scaling to the number of UEs is actually closely related to how much resource budget we have, because if the RAN resource or the server GPU budget is above what we can handle, we can't guarantee the latency SLO at all. But To some extent, I completely agree. Our current evaluation is mostly within like 10 UEs, but if we want to extend it to more number of UEs, we need a more complex resource estimation algorithms and also resource allocation across UEs. But we believe it is possible, but I guess it has much more challenges. So yeah, I'll try to work on that as well.
Thank you for the great talk. This is Shiming from Hong Kong PolyU. And I have a question that I noticed in one of your slides, your system mainly target that for the video analytics applications that the computational workload can vary with time and the communication bandwidth between the camera and RAN is relatively stable. And my question is, for such paradigm with the app-RAN mutual awareness, is it possible to work for another kind of a scenario that the communication bandwidth can vary with time, but the video analytics workload is relatively stable? And does this paradigm can help for that applications like the high mobility with the edge devices and to improve the video transfer or video analytics performance for these scenarios? Thank you.
Oh, sure. Thanks very much for the great question. So actually, yeah, the example that I presented here is, as you mentioned, the network bandwidth is stable, whereas the workload is fluctuating. There can be converse cases. For example, the vehicle is driving at a very fast speed, so network bandwidth fluctuation is quite high, but the scene content is relatively simple. And actually, our solution can also handle such cases because the bitrate DNN interplay is a bidirectional adaptation knob. For example, like I mentioned only one path here, but you can, for example, in the driving cases, I guess we can use a more heavier DNN model, but use a smaller bitrate so that it can be more robust to bandwidth drops and so on. So I think, yeah, we believe that we can handle like diverse fluctuation scenarios, but actually some practical deployment with it, I am sure that it will incur additional challenges. So yeah, I think there's more to look at into related to that. Thanks for the question.
Thank you for the insightful discussion.
All right, thank you so much. Thank you.
Thank you.
All right.